All right, today we are diving deep into one of the biggest puzzles in AI right now, the efficiency puzzle. You see, we've got these incredibly powerful large language models, but they're notoriously expensive and, frankly, kind of slow. So the big question is, how do we make them fast and affordable enough for everyone? Let's get into it. It's the question every single developer and business leader is wrestling with. You've built this amazing AI, but actually deploying it for real users feels like trying to fuel a rocket ship with solid gold. The costs just spiral. The user experience lags. Why is it so hard? Well, the heart of the problem is a process called inference. Now, think of it like this. Training a model is like sending it to school to learn everything. But inference, that's the live performance. That's the moment you ask it a question, and it has to think on its feet and generate an answer. And that live part is where all the day-to-day costs come from, and it's surprisingly difficult to do well. So what are the technical gremlins causing all this trouble? Well, every time a model generates text, it needs to remember the conversation's context. It stores this in its short-term memory, which is called the KV cache, and this thing is absolutely enormous. Trying to handle tons of users at once, what we call batching, becomes a logistical nightmare, and the old ways of doing it waste a shocking amount of precious GPU memory. These are the core problems we've got to solve. Okay, so how do we start solving this puzzle? The very first piece is what we call the serving engine. You can think of this as the high-performance operating system for your AI model. It's the software that controls how your model runs on the hardware, and picking the right one is absolutely your first critical step. Now, in the open source world, two giants really dominate the scene, VLLM and Hugging Face's TGI. And they represent two totally different ways of thinking. VLLM is all about maximum throughput. It wants to get the most work done over a period of time. TGI, on the other hand, is built for maximum responsiveness. It wants to be the fastest off the starting line for every single request. VLLM's secret sauce is this incredible innovation called paged attention. It basically takes a concept that your computer's operating system has used for decades, virtual memory, and applies it to GPUs for the first time. By managing that massive KV cache in tiny, flexible blocks, it almost completely eliminates wasted memory. And that lets VLLM pack way more user requests onto the very same GPU. And the result of all that cleverness? Well, under heavy real-world conditions, studies have shown VLLMs can achieve up to 24 times the throughput of TGI. I mean, that's not just a small improvement. That is a revolutionary leap in performance. And you don't have to take my word for it, just look at the numbers. This chart says it all. For a Llama 2 model with lots of users hitting it at once, TGI maxes out around 4,000 tokens per second. Not bad, but VLLM with its paged attention just screams past 15,000. It's playing a totally different game when it comes to raw throughput. But hold on, it's not a simple knockout. There's a really important trade-off. TGI is often faster at generating the very first word of its response. This makes an application feel super responsive, which is fantastic for things like interactive chatbots. VLM, though, is faster at getting the entire job done from start to finish. So you have to ask yourself, what's more important for my users? A quick hello or a faster final answer? Okay, so that was puzzle piece number one. Now for the second piece. We've optimized how we run the model, so let's optimize the model itself. The key technique here is called quantization. It's a fancy word, but it just means shrinking the model, putting it on a diet, really, to make it smaller, faster, and cheaper to run. But this is where the fear has always kicked in. For years, the developer community has been frankly terrified that if you shrink a model, you'll break it, that you'll sacrifice its intelligence just to get more speed. This feeling was captured perfectly in the title of a recent research paper, Give Me BF16 or Give Me Death, with BF16 being that full-fat, full-precision format. So this is the million-dollar question, isn't it? Does quantization, this process of using less precise numbers to represent the model's brain, actually make it dumber? Does it hurt its performance on real tasks? For a long time, the answer was kinda yeah, but the latest techniques have completely changed the game. Okay, get ready for this because the data is pretty mind-blowing. On a standard coding test, the full precision model got about 80% accuracy. Makes sense. But look at the smaller versions. The 8-bit model is basically identical. The other 8-bit version is just a smidge behind. And then, this is the crazy part, the tiny 4-bit version is actually more accurate. So the big takeaway here is pretty clear. With modern methods, that old fear of accuracy loss is basically a myth. The 8-bit formats, they're essentially lossless. And even the super compact 4-bit formats are incredibly competitive. The technology has just gotten that good. So now we have our two puzzle pieces, right? We have an efficient serving engine, and we have a lean quantized model. So let's snap them together and see what kind of real-world dollars and cents savings we can actually get. First up, let's look at a synchronous deployment. This is when you're handling just one request at a time. It's really common for apps that need the absolute lowest latency possible for a single user. And in this case, the choice is surprisingly simple. And this table just perfectly illustrates the power of putting it all together. For this kind of one-at-a-time job, that tiny 4-bit quantized model is an absolute monster of efficiency. On a 70B model, you get 2.4 times more queries for every single dollar you spend. And on a massive 405B model, it jumps to a 5.5 times cost reduction. That's 5 times the work for the exact same price. Just incredible. But things get a little bit trickier when we switch to an asynchronous deployment, when we're serving lots and lots of users all at once. Here, the answer for which format is best, well, it turns out it actually depends on the GPU you're using. Now, this is where it gets really nuanced and interesting. On a mid-tier GPU, like an A6000, that 4-bit format is still the king of the hill, giving you more than a 3x speedup. But when you move up to the big guns, the high-end A100s and H100s, the 8-bit formats actually take the lead. They're just better at using all the raw power those top-tier chips have to offer. So, with all these moving parts, how on earth do you actually make the right call for your project? Let's boil it all down into a simple, actionable blueprint you can use. It really comes down to just 4 questions. 1. What's your use case? Do you need that snappy, interactive feel of a chatbot or the raw power of batch processing? 2. What hardware are you working with? 3. Based on that use case, pick your framework. TGI for responsiveness, VLLM for throughput. And finally, number 4. Pick your quantization format based on your hardware and your deployment type. And that's really the main takeaway from all of this. There is no magic bullet. There's no single best solution that works for everyone. The most efficient, the most cost-effective setup is always going to be a custom-tailored combination of your framework, your quantization, your hardware, and your specific use case. Which leaves us with one last big, important question to think about. As these AI models continue to grow at an exponential rate, are all these efficiency techniques just nice little optimizations? Or are they quickly becoming an absolute necessity? Maybe even a matter of survival for anyone who wants to build with AI at scale. Thanks for tuning in.